have a quick overview of Mallett, and then we'll get into our webinar on thermal analysis. And at the end, of course, we'll have time for discussion and questions. Feel free to type into the chat box anytime if you have questions during the presentation. Steve will attempt to work those answers in. And at the end, if you have questions, let us know. I will be recording the today's webinar as usual, so if anyone would like a copy of the recording, just let me know. Mallett Technology is a world-class engineering software. We use world-class engineering software and tools combined with our broad knowledge and expertise to help our clients compete in today's marketplace and produce reliable and cost-effective products. We've been doing this for over 40 years in the engineering consulting business. We started as the consulting arm for Swanson Analysis Systems, which was founded by John Swanson as Swanson Engineering Associates Corporation in the mid-70s. We've been an ANSYS channel partner since 1985. Our website is www.mallett.com, of course. We will have more webinars, and we will keep them on Fridays at 11 a.m. As always, I'll send out invitations to everyone, on what the upcoming webinar subjects will be and when the webinars what days they'll be on. Also, I encourage anyone who's on the webinars, feel free to email us if there's any subject you'd like us to cover in the webinars. If it's something we have not covered and you'd like us to cover it, feel free to let us know. If it's something that you're interested in and we have not covered it, we'd be happy to entertain that. So now I'm going to turn the presentation over to Steve. And we can get started with our webinar today on thermal analysis.
Okay. So thanks again for everyone joining. Yeah, like Bud says, we'll talk through thermal analysis. I'm going to go through kind of some basic background on how ANSYS handles thermal analysis, and then I'll just walk through a couple example problems I set up to highlight different features within the software and different ways you can set up a model and different considerations when setting up a model. So feel free to chime in if you have any questions. And yeah, we can get started. I expect this one, I know my past few webinars have been more in like the hour time frame. I expect this one will be a little shorter. So jumping right into the slides. So when we're talking thermal analysis or heat transfer analysis, there's essentially three basic modes of heat transfer, right? There's conduction, which is heat transfer between bodies in contact. There's convection, which is heat transfer between a body and a surrounding fluid. And there's radiation, which is heat transfer from a body or between bodies by electromagnetic waves. So this can be from a body into ambient air. It can be between solid bodies. Just depends on how the problem's set up and what considerations there are. Generally, I find that in pretty much any thermal analysis I do, all of these are in play, right? What I often find, though, is that depending on the temperatures I'm dealing with, usually conduction will dominate a problem, and convection and radiation are smaller pieces. But once again, from my perspective, I always include essentially all the sources of heat transfer. And then if I'm finding, let's say, for instance, I have a large problem and radiation is not really contributing much to the solution, potentially you could eliminate radiation to increase your problem speed, because that would make it potentially a linear system at that point. But once again, it's engineering judgment. It's better safe than sorry in terms of having all the different heat transfer methods in the analysis. So just some heat transfer basics, right? So conduction, it's just defined as the thermal conductivity times essentially the change in temperature for a given direction. The one note here is heat transfer conduction flows from hot to cold, right? We can represent this as a thermal resistance, which is equivalent to length divided by the thermal conductivity of the material times area, right? This is oftentimes we were simplifying a system to something equivalent, let's say an equivalent circuit diagram, right? This is how we calculate the resistance of a given material. And then we have convection, right? Convection is transfer between a body and a fluid. The big piece here that can oftentimes be challenging to determine is the convective film coefficient, H, right? So this is not a material property inherent to materials, right? This is a coefficient that depends on a number of factors, primarily, well, it depends, right? If we're talking free convection, so free convection is where you don't have forced air blowing over a system. Then it's dependent on the geometry, it depends on the orientation of the geometry, it depends on the difference between the body temperature and the fluid temperature. And there's forced convection, which depends on the rate at which air is being, well, the rate at which the fluid is being forced over the body. Once again, depends on geometry, all these different factors, right? So generally, a lot of the problems I'm dealing with on a regular basis are usually free convection. It's usually let's say an extrusion press, for instance, that's just hot because it's having to make metal malleable. So oftentimes there I'm looking at what's the free convection on external surfaces, right? And there are ways to do this. ANSYS, and I'll show you, has tools to that automatically calculates this based on a number of assumptions. But generally, I like to assume, essentially, if I'm dealing with natural convection, it's almost always going to have a convection coefficient between 4 to really 7 watts per meter squared degrees C. And usually I'll find that if I vary that, oftentimes it has limited impact on the overall solution in terms of the overall temperature distribution. And then last, so radiation, right? Radiation is inherently nonlinear because of this T to the fourth term, right? So this is just radiation from a body. All bodies radiate heat, unless you have all bodies radiate heat. So the key here is Stefan Boltzmann constant, defined automatically in the software. Emissivity, so this is what we as a user would define in the software. Everything else, ANSYS is automatically going to calculate. So when we're looking at emissivity, that's just the ability of the body to radiate energy well, right? Essentially, as you vary emissivity, the amount of heat that's radiated from a body is going to increase or decrease. ANSYS deals with radiation particularly on the surfaces of bodies, right? It's not necessarily interested in any internal behavior of the body. It's only on the surface or from surface to surface. And I'll show you how to set this up. You can set it up between bodies in an enclosure. You can set it up so bodies radiating to each other have different emissivities, radiating to external temperatures, all that stuff. Okay, so just continuing on with the basics. So from a first law of thermodynamics perspective, right, we know that to be able to solve or to have a cohesive thermal problem, essentially our energy stored plus our energy in through any boundary plus energy out through any boundary plus the energy generated has to equal 0. Right? If this does not hold true in your analysis setup, the analysis is not going to converge. I'm not going to go into more detailed math here. So potential problems of thermal analyses, and this is really just generalizing kind of the most often encountered. So the first and foremost is potentially the simulation could just be poorly constrained, right? So if we look at let's say a static structural simulation, we know that all translational and rotational degrees of freedom have to be constrained to solve that problem. So the degree of freedom that thermal analyses deal with is temperature. And so we have to have temperature constrained somewhere in the problem to allow that to be solved. If it's not constrained, that's essentially equivalent to rigid body motion. So big deal here is just make sure if you're running a thermal analysis that it is constrained. If you're having errors, check that it's constrained. If it's not, add a constraint, and then and a constraint doesn't necessarily have to be a set temperature. It could be a, let's say, heat flux out of the body, but there has to be some boundary that allows heat to leave the system. Because otherwise, you can imagine if you have heat generated in a system and there's no way to leave, it's essentially the heat is going to continue to increase into infinity, and it's not going to be able to be solved. The next potential problem is large thermal gradients or flux singularities, right? So let's say, for instance, you had a point heat source, right? You can imagine a point heat source is going to be similar to a point load in a static structural simulation. And so at that point, you're going to get infinitely increasing temperatures as you refine the mesh. Additionally, depending on your geometry, you can get non-physical thermal results. These are things just to be aware of, right? This is generally when you're developing your mesh, ideally you're taking these into account at that point in the process rather than later. But usually, and I'll say, thermal analyses are generally easier to solve than static structural analyses. The biggest reason being is that you're dealing with 1 degree of freedom rather than 3 in the case of solid elements or 6 in the case of shell elements. So generally here you can kind of blast the thermal analysis with many more elements than you would in a static structural, and it is almost guaranteed to solve unless you have some nonlinear behavior going on that you have to kind of work on the convergence. And I don't know if I talk about it later, but real quick, so from the nonlinear perspective, right, what makes a thermal analysis nonlinear could be nonlinear material properties, it could be a nonlinear convection coefficient term, it could be radiation. There's really a number of factors that could make it nonlinear and kind of have to force you to deal with convergence. Okay, so briefly, I'm going to just touch on what geometry types are supported in thermal analyses within ANSYS. And the long and short of it is all geometry types are supported. There's a couple different considerations, though, to make when dealing with certain geometry types. So both 2D and 3D are supported with regards to shell elements. So if you're using shell elements in a thermal analysis, the solver assumes a uniform temperature through the thickness of the shell body, right? So you can see here we do get changing temperatures kind of tangential to the shell body, but through thickness, the temperature is going to be constant. The same is true for line geometry, right? So this is line geometry with section properties assigned. So beam or truss structure or anything along those lines. Essentially, you're going to get change in temperature along the line body, but not through the section of the body. Okay. So then let me touch on how contact is kind of dealt with in ANSYS's thermal analysis. The way in which contact is dealt with, essentially, if something is in contact, and contact is defined as inside or outside of the pinball. So inside of the pinball, it's in contact. Outside of the pinball, it's not in contact. If it's not in contact, you're going to get no heat transfer taking place. If it's in contact, then essentially you're going to get conduction occurring. And depending on how you set it up, it could either be perfect conduction where there's no resistance at the contact, or you can actually insert some contact resistance to make the problem more realistic. The reason, so you can use any type of contact from bonded to no separation, rough, frictionless to frictional within the thermal analysis. Generally, the reason you would see these types of contacts included is if you're leveraging the exact same model setup for a thermal analysis as a structural analysis, then you might want to use frictionless or frictional or rough in place of like a bonded. If I have a thermal analysis that I'm not essentially directly using in a structural analysis, there's essentially no need to use any of the last three, right? Usually you just use bonded no separation because you're essentially just telling the solver, hey, there's conduction at this interface. It's just when you want to share a model setup that you'd use kind of more nonlinear contacts. Okay, so this is what I mentioned earlier, right? So whether or not there's conduction just depends on the size of the pinball. You can see here as we get away from the pinball, or away from, if the geometry is further apart than the pinball size, we're not going to get conduction between these nodes, etc. on the outside. But when it's within the pinball size, we will get conduction in this area. So the pinball is always automatically generated, right? So if you want better control of your model, you can go in and manually specify the pinball, right? And then you get this blue sphere that kind of shows you, hey, this is the pinball size that you're recommending or you're telling the solver to use. Okay, so from thermal contact resistance. So thermal contact resistance is pretty common. Generally, let's see. It's a safe assumption for a welded contact not to have thermal contact resistance because you're essentially joining material together. Or if there is resistance at that weld, it should be pretty negligible. But everywhere else, it's fairly readily assumed that there's going to be some amount of resistance, right? Resistance can be from a number of factors. If you don't have a flat surface, you're not going to have good, or let's say you're not going to have perfect conduction across that interface because essentially conduction will occur across the peaks of each side of the interface. Same rationale for the finish. Oxides potentially could induce a surface material that is or more resistant to conduction. If you have fluids in the center, once again, you have another thing that to conduct heat through. Contact pressure, higher contact pressure, you're going to have better conduction. Less contact pressure, you're going to have lower conduction. You can imagine if I have an infinite amount of pressure at an interface, that's essentially a uniform material at that point because you're essentially just compressing the material until it's perfectly flat and perfectly meshed with the opposing material. Surface temperature and then conductive grease. So conductive grease would be commonly used for like PCBs, right? If you have a heat sink, a conductive grease, while it's meant to help conduction, right, there is some amount of thermal resistance associated with that. And so ANSYS does allow you to specify that resistance. And actually, one more thing, what you'll typically see if there is thermal resistance is you'll see a delta or a drop in temperature across an interface, right? You're not going to see a consistent temperature across an interface. You're going to actually see a delta. So ANSYS does allow you to account for this. If you use the bonded contact setup, right, there is a thermal conductance value that you can specify for a particular bond. This is essentially the same as thermal contact resistance, just requires you to modify in terms of invert and multiply by that area to get thermal resistance from the thermal contact conduction. The one note here is to have this thermal contact conductance value available. You cannot use an MPC contact formulation. MPC is similar to shared nodes, and essentially it creates a formula saying that the two different sides of the contact must change together, right? So there's no option there to have a delta T or temperature drop across the interface. So Just make sure if you're trying to find this, you're not trying to use MPC contacts. Okay. So those are all the basic slides, and then I set up a couple examples that I just wanted to walk through in terms of the setup and then potential considerations. So let me look at the workbench workflow first. So with any thermal analysis, you can always transfer those results into structural analysis. It's really easy, really straightforward. All it looks like is you have your thermal analysis. You're going to grab this solution branch and then drag and drop it to the setup. Right? What that's going to do is it's going to allow the structural simulation to say, hey, I have some load coming in. I need to be able to import the body temperature that's specified. So you can import that, and what the structural solver is going to say is, okay, I have this temperature distribution on my body, and as long as you have a material property value of coefficient of thermal expansion for each material in the domain, in which you have to have if you're going to have temperature or thermal loads applied. As long as you have that information, it can use the thermal expansion coefficient values to calculate resultant stresses from the applied temperature. Okay. And you don't have to fully share models here. All right, I'll show you a little bit later that I have similar geometry but completely different meshes, and you can still transfer thermal loads from a steady state or transient thermal analysis to a static structure or transient structural analysis. Okay. So this is just a dummy analysis I set up. This geometry is essentially meaningless. You can see I essentially just have some weird looking standing body inside a dome. There is mild insulated material on a portion of the dome, while the rest is just structural steel. All right, and then I have just a plate on the bottom that everything's resting on. So the one thing I'll call out before going into kind of applied boundary conditions is another option, right? So you have two options when talking about conductance and getting heat to transfer across interfaces. Right, the first is kind of what we've talked about in the slides, which is you can use contacts to specify two bodies transfer heat to one another. The second option is to use shared topology, let's say within space claim. Shared topology tells ANSYS that when it meshes to interfaces, it has to use shared nodes across that interface, which is what I did at this interface between this cone and the plate. Right, you can see all those nodes are shared. You're going to get, this essentially allows you to get really good temperature distribution across an interface. However, you cannot at that point specify any type of contact resistance. Right, so that's the drawback. But if you're convinced that you have really good conduction, then generally I recommend shared topology as much as possible. Partially just because it simplifies your model, it simplifies the structure tree, and generally something simpler, there's less risk of error. So if we just step right into the boundary conditions, so you can always apply, well, let me look. So a number of options, right? You can apply temperature to a body. If you apply temperature, the solver will maintain that temperature. It'll either input the amount of heat it needs to stay at the temperature, it will remove the amount of heat that needs to stay at that temperature. Convection, right? This is heat transfer between body and fluid. Usually this is, well, in a lot of problems, it's just transferring to ambient air. Radiation, if you have hot enough bodies, this will become a dominant term, right? That T to the fourth does dominate if you have large temperature differentials at hot temperatures. So you can specify radiation. You specify heat flow. So heat flow is just watts across a boundary, right? Whereas heat flux would be watts per meter squared. You specify internal heat generation. So this is watts per meter cubed, or perfectly insulated. The perfectly insulated essentially is a adiabatic condition. If you do not specify a contact in an ANSYS thermal analysis, that's equivalent to an adiabatic condition. ANSYS does not assume that heat transfers across boundaries. It only will transfer heat exactly where you tell it. So in this analysis, I have temperature defined on kind of my internal hexagonal rods. I have radiation defined. Yeah. On all the exterior surfaces of this standing object. You can see I've specified an emissivity here for this object of 0.5, and I specified an enclosure number here of 1. The reason I did that is because I want actually one more thing, and then I specified this is radiation between surfaces, right? So I could, if I left the problem set up as it is now, I would have all these bodies would radiate to one another, right? So I could have radiation between these surfaces, I could have radiation between these surfaces, et cetera, anything within the field of view. However, I wanted to specify radiation to between those surfaces as well as between those surfaces in the interior of this dome, right? But my dome has a different emissivity to essentially generate another radiation boundary condition. And then I specify its own emissivity, but I specify that it's also for enclosure 1. So then when the solver goes to generate and set up the problem, it's essentially going to say, hey, we need to grab both of these radiation conditions, combine them together, and radiate between all the surfaces specified within. Then I have a temperature condition on the exterior edge. This is a cold temperature, so essentially it's going to be drawing heat out. It's a heat sink. I have radiation to the external air, right? And you can specify ambient temperature however you want. And then I have convection to the ambient air on all my external surfaces. The one other thing I set up is for the contact between the tall rod holding up the rest of this hexagonal internal body, I do have a specified thermal resistance or thermal contact inductance of 500 watts per meter squared degrees C. And so what you're going to see is as a result of that specification, if I look at my temperature profile at that interface, you can see I have my specified 500, and then you can see it immediately drops across the interface, right? 500 to essentially immediately 450. And I can make that a little bit more evident. So you can see that immediate temperature drop, right? Fully red to 450. That's a result of the thermal conductance value. Whereas where I have perfect conductance, which is all the other contacts, or my shared topology, I get a perfect gradient across all boundaries, right? There's no temperature drop here. It's nice and consistent, as we'd expect. Okay, so the one thing I did want to show is if you don't want to go through the hassle of using hand calculated values to come up with a convection coefficient, right? ANSYS does offer a couple of assumed formulaic guides to what this convection coefficient may be, right? To look at those, all you do is click on film coefficient. You can hit import temperature dependent, and then at this lower side you have a couple of assumed formulas and assumed curves for different geometry setups, right? So you can see you have a horizontal cylinder, you have vertical planes, you have stagnant water, etc. Right? So in this case, I'm going to say, okay, I have a vertical plane. What that does is that essentially creates a nonlinear curve where I'm looking at temperature or convection coefficient as a function of temperature. This now immediately makes this it was already nonlinear because of the radiation, but if you did not have radiation, this problem now immediately becomes a nonlinear problem. And you can have the convection coefficient vary by a number of things, by the average film temperature. You do the difference of surface and bulk temperature. Bulk temperature would be the air. You just do the surface, just the bulk, etc. This is helpful, but what you may see is for a very large range of temperatures. So this is almost 0 degrees C to 1,000 degrees C. My convection coefficient a little bit more than doubles, from roughly 4 watts per meter squared degrees C to 8. And what you'd often find is if you run cases with 4 and then you run cases with 8, you may find that there's very little difference in the resulting temperature distribution, in which case maybe you decide that the additional heartache generated as a result of this being more nonlinear and having to kind of iterate along this curve, maybe it's not worth it, right? But leave that to engineering judgment. Okay, so that's all boundary conditions, right? So the biggest difference between a steady state thermal analysis and a transient thermal analysis is for the steady state, you have to have a heat sink. You can't infinitely generate heat within one body because your temperature is going to rise infinitely and you're not going to be able to solve it from a steady state perspective. For a transient thermal analysis, you do not need to have a heat sink, right? Since you're looking at it from a time perspective, the solver is essentially going to calculate that infinite rise in temperature. So it's not required, right? So here I have a similar analysis, and the big difference with the transient thermal analysis is you're dealing in time, right? And so you just need to specify in your load steps what time you're looking at. In this case, I have only one load step, and it's going from 0 to 1,000 seconds. And I'm allowing, in general, and I would recommend this if you're doing transient thermal analyses, oftentimes the automatic time stepping algorithm is very beneficial in solving the problem in the most efficient manner possible. So it's highly recommended. Take advantage of it. You can certainly try to do it at a fixed time step and see what the difference is, but just be warned, it may take a while depending on how you set it up. But so really the big difference here is you just have to specify real time, and oftentimes in this case here, rather than a set temperature, I have internal heat generation specified on these tubes. So I'm essentially injecting a certain amount of watts into the system. So I have a heat rate into the system, which is going to slowly heat it up. If I had a set temperature, typically, well, depending on how I apply the temperature, it may be harder to solve, right? If I apply the temperature in a step change, from a transient thermal perspective, that's much harder to solve and converge to than a much more gradual temperature change. And you could have a very steep gradual temperature change, but as long as it's not a step, and as long as your time steps are small enough to capture that gradual rise, it can be solved. But a strict delta in temperature is incredibly challenging to converge. Okay, so let me pause for a sec. I've jumped between a lot of different topics, a lot of different things. Are there any questions with any of the things I've talked about? Okay. So the one other thing I'm going to cover is importing loads. So I mentioned here earlier, so I have, let me make this a little more obvious. So you can see here I have a steady state thermal system, and I'm sharing my engineering data and geometry with that system, right? And then I'm importing my thermal load. Sometimes you may encounter problems where you want either different contacts or different mesh criteria for a given model, and so maybe you won't share the mesh and the contacts and all that data between the two. So in this case, I decided I wanted a much finer mesh on the body than I did in my thermal analysis, and additionally, there were certain pieces of bodies that I wasn't interested in, right? So this could be in the case if for a thermal analysis, I am physically representing insulation. When I'm bringing that thermal data to a structural analysis, usually depending on the installation you're dealing with, it's not going to have, insulation does not have a large stiffness, it's not going to have a large impact on the overall structural response of a system. So generally it's not beneficial to represent insulation in a structural analysis, right? So in that case, I wouldn't share the mesh, and when I come to my static structural or my transient structural analysis, I would actually suppress that body, and then I can, when I'm importing my load, I can specify I want to import loads on only the specified bodies. So here there's 4 bodies here. This solver comes in, looks, says, okay, based on a number of factors, right? It's looking at volume, distribution centroid, bounding box, and then combination of the two. As long as these things match to within a certain degree, it's going to transfer the temperatures to that body. And if I have different mesh sizing, which in this case I do, it's going to interpolate where the temperature should be at each node of each element based on the distribution calculated in thermal analysis, right? So if you're ever trying to import temperatures in a case like this and you're having issues, right, one thing you guys do is you could increase the tolerance. This will allow it to have a little bit more freedom in terms of figuring out which body to apply the temperature to. And then if you're continuing to have problems, I would dig a little deeper into this imported load transfer summary to see really what volume differences it's dealing with, what differences it actually seeing between the bodies you're trying to transfer the temperature profile between. Okay, so I'm going to stop there because that's a whole lot of information over a whole broad spectrum of potential use cases. So for anyone on the phone, is there any questions with anything I covered?
And the chat box has no questions either, Steve. So if anyone,
yeah, we can wrap up then.
Feel free to contact us if anything pops up afterwards. Again, feel free to drop me a note if you would like a recording of today's webinar for yourself or for a colleague that you feel may be interested. I will also send out news of our next webinar as soon as that is available. I'll send it out to everybody. And as always, when anyone gets it, feel free to send it to any of your colleagues that may be interested in the webinars. So if there's nothing else, Steve, thanks again for all your work today. And everyone have a good weekend. Thank you.